This video, we're going to start discussing differentials. There's a few different things that you can do with them. But the first thing we're going to do is kind of look at a more generalized version of Newton's method, and that's to approximate the value of a function at a specific point. And this can be any point, not just when you're looking for zeros. So this approximation is given here. We are saying consider the point-slope form of a line. It is differentiable at some point. And so we have that the difference in the y's, so y minus effectively, y minus y1 is equal to m, the slope, times x minus x1, where you have the point x1 comma y1. Okay, same thing here, except for you're taking a look at the value of x equals c. All right, that's the only difference. So you're saying just this y1 is just a function value at c. The slope, however, is now the differential. And what this does is if you have a general function, and so I'm just going to draw a curve here, one that comes up like this and just over. And now if I have a point here that I'm looking at, and I want a tangent line to that. Okay, so here we are tangent at that point. Well, you'll notice there's a little bit of difference. As you get really close, there's not a heck of a lot of difference between the value of the tangent line and that of the function. But as you get further and further away, there's quite a bit of difference. Well, that's what this is. It's basically an approximation. Many functions look quite nasty and are difficult to work with. However, if we can get a good tangency from them, then locally we can say, oh, well, it's pretty close to this. And I'm telling you, applied mathematicians, physicists, chemists, engineers, oh, they love this stuff because this saves them just a ton of work. Plus, they might not know exactly how the function behaves, but they might know how it changes. In other words, they might understand what the derivative looks like, but not really understand what the function looks like. That's especially true when you get to multivariate, and we don't really want to go there yet. Enough scaring you. If they're sufficiently close to c, you can approximate the value of the function. And this is called the linear approximation of the function at c. Okay, this is only good for a certain point. After that, you kind of have to recalculate it. And this is what usually takes scientists and engineers so long to do something, is that they might not know what the function looks like, and so they have to do this several times to kind of map out what the function does. That takes a lot of supercomputers a long time. And so it takes quite a while to say model a supernovae, or perhaps model a particular construction of the universe, or how a car will behave in a crash, that sort of thing, because they can tell you what it's going to change like, but all they have are these little linear approximations, and so now they have to build a function out of that. Okay, now here's just a quick kind of simple example. I'm saying, okay, let the function be x to the fifth. And you may not know what the function looks like. You may only have what the derivative looks like. And so that's not so bad, I suppose. Okay, but now you have this constraint of, oh, look at this point. Okay, well, fine. Then if we look at what the function does around the point x equals 2, first we take its derivative. And so we simply have y minus f of 2 is equal to f prime of 2 times the quantity x minus 2, because 2 being, of course, the value of the number, or the x value that we're considering. So now if we graph that, we have 8, or not graph, but if we solve that for y, we have y is equal to 80x minus 128. And this is going to be our tangent line. And so we're going to kind of take a look at how this gets close and kind of how good it is. All right, well, I've already done the Excel for it. And so I'm just going to kind of run over here, and again, this is kind of nice for me, or easier for me than using the calculator. And so I've started at 1, and I've moved closer and closer to 2. You'll see I've also kind of started shrinking my my intervals. And so at 2, they're exactly the same. As you move away from 2 just a little bit, they start kind of becoming quite a bit off. Okay, but as you move further and further away, I mean, they are really off. And so this linear approximation isn't that great as far as that goes. At x equals 2, the slope of the line is very significant. And because it's very significant, then our linear approximation starts petering out. But this is the idea of the linear of linear approximations. They are point specific, and so every time you change the point, you have to redo the approximation. That's one of those things that just takes forever. Okay, a computer can do it very quickly, but when it has to do billions and trillions of these things just to get a good feel for what the function is doing at each and every point, that takes a long time. And that's where you get your big problems in as far as modeling. So that's linear approximations and how differentials work in that case.